Hi, Ben.
Ben.
So, Ben, I'm sitting up front today so that you can hear my voice a little bit more.
Yeah, Ben, I'm actually really...
Because that's exactly what you want to do.
Wait.
Yeah, I will.
Bracket.
Basketball.
And future years will be like, oh, it's March Madness now, too. Plus, you know, it's Friday, March 22nd, 2019. Hi, future me. Okay. Rule number 1, we know that b to the x times b to the y is b to the x plus y. We've been doing that one for a while. But what I want you guys to kind of backtrack on and really understand is that what we've created is something much more valuable. It's an operation that is transforming multiplication into addition. Stop for a second, because this idea is a part of the bigger picture of logarithms. It's an operation that is transforming multiplication into addition. The multiplication of the basis becomes the addition of the exponents. And so what part of the purpose of a logarithm is when we do the reverse of this rule. And the reverse, in a way, we'll call this reverse 1. This is actually the log rule here, is that if I take the log base 2, I'm just going to use 2 as an example, of x, plus the log base 2 of y, I get the log base 2 of xy. You actually saw this before a while ago. There was a problem. I told you that this would come back. Now we're here. That actually it was this same problem, log base 2 of 8 plus log base 2 of 4, and it wanted you to show that that was the same as log base 2 of 32. Sorry, I'm writing 32. Unlike my period 5, I'm actually going to write underneath here and sort of explain this one a little bit more. This is the log base 2 of 2 times 2 times 2 plus the log base 2 of 2 times 2 equals the log base 2 of 2 times 2 times 2 times 2 times 2. And I want you to have a little bit of an intuitive sense about why this is working. Because how many 2's do I have there? I mean the first one, 3. How many 2's do I have here?
3, 2.
And how many total 2's do I have here? And yet, when you look at it from this perspective, it becomes a little bit evident. 3 plus 2 equals 5. When I look at it from the above perspective right here, it seems like almost magic. Like you're not really sure why this is working, but it does. That is the whole schema of this. A log is an exponent. And when we add exponents, it has the same effect as multiplying bases. And that's why this is the reverse. By adding exponents, we are in fact kind of multiplying an argument, of kind of multiplying something we're taking the log of. So given that, the applications of this are going to be huge. And when we get a true hour period, like Monday, I want to show you how an addition of logarithmic distances can translate to multiplication. How this distance and this distance can mean something that we're actually multiplying, which is very, very different to think about measuring a distance and having it actually be a product. But if that distance is measured in a logarithmic scale, that's precisely what it can be. Rule 2 we're going to do really quick because I want you to see this second rule in conjunction with the first. Since it's basically the same rule, 2 to the x divided by 2 to the y is 2 to the x minus y. Can you take a second while I pause this and underneath write down the same rule as reverse 1, but let's call it reverse 2. And I want you to write the version of this that would be like change some things around and make this the same but opposite rule. I don't think I said that right, but I think you know what I mean. All right, back to this. The reverse of rule 2 is to say that the log base 2 of x minus the log base 2 of y equals the log base 2 of x divided by y. Now I'm going to create a little note underneath we're going to apply to this in a couple of days, but I need to, like there's a big, we have these things in math books sometimes where they're all like misconception alert, so this is one of them. So I'm going to put a little asterisk. This does not mean that the log base 2 of x minus the log base 2 of y equals the log base 2 of x over the log base 2 of y. This does not mean that's true, because that's decidedly not true. That happens a lot, that people will mistake this. I'll kind of slide this down here. This is a big fat no. That's not a thing. That second one is a thing, but it's not that thing. It's something else, and we will deal with what that is. But that's not much later, but it is a little later. Okay, I want to show you some of what you're going to do before we get to the third rule. There were three. We have to do the opposite of the power of powers rule, and there is one. But for example 1, the directions that you're going to see are basically going to say this: write as a single logarithmic expression. I'll put single log. Write as one logarithmic expression. So to start, this can actually become a way to combine multiple logs being added into one of them. So here's an expression. Expression's a thing with no equal sign. And I want to bring that into a single logarithmic expression. How do I do that? Log base 7 of 4x plus 4. Can you make an adjustment to that? That would actually be the log base 7 of x plus 1 plus the log base 7 of 4 minus the log base 7 of 8. What's an adjustment that you can make to this that would make this expression happen? We want a single logarithmic expression, log base 7 of, what would it be? Good, 4x plus 4 over 8. So where subtraction becomes division, and you can actually simplify that one now. Log base 7 of x plus 1 over 2. Now, let's say that we grouped this together. I actually want that in a different color. And let's say we did that first. Does that change anything? If I take 5 plus 1 minus 3 and I group the 1 minus 3 together, does that actually change anything? No. And yet if I group these together, I get the log base 7 of what? 1/2. And 1/2 times x plus 1 is this. This can happen in any order, and you should still maintain your equality. Let me hit a different example, and we're going to change the directions on this one. I want you to solve. Actually, this is poor notation. Let's just kind of do number 2 here. Solve log base 7 of x plus 1 plus log base 7 of 4. And instead of saying minus, we're going to say equals log base 7 of 8. We combine those. I want a single logarithmic expression. Log base 7, 4x plus 4 equals log base 7 of 8. Now what? Herschel? Mm-hmm. Yep. We're going to use the word, and it's okay if you don't remember this one, we're going to use the word argument for the thing inside the log. We're going to make the arguments equal to each other. This is the argument. 4x plus 4 equals 8, which would mean that x would have to be uno. Something you absolutely have to do, at least in your head, plug 1 back into the original. Make sure you're not taking the log of a negative number. That won't work. Make sure your base is not equal to 1. And it's not 0, and it's not a negative number. Bases have to be positive, not 1. So that will keep coming back in a little bit, but not just yet. Big break line, we're going to go to rule 3. We're going to wrap this up with the third of the 3 log laws. Rule 3 is this. B to the x to the y equals reverse 3 is a weird one. Here's reverse 3 in kind of a little bit of a simple way. Log base 2 of 32, which I can write as the log base 2 of 2 to the 5th. This expression is saying, how many times do I have to raise 2 to get to 2 to the 5th? How many times? 5 times. I do this 5 times. It's actually 5 times the amount of times it would take to raise 2 and get it to 2, right? To take 2 and get it to 2 would be 1 time. To take 2 and take a 2 to the 5th would be 5 times. 2 to 2 is 1 time. 2 to 2 to the 5th is 5 times. This 5 times, the reason I'm saying 5 times so objectively is because I'm actually saying 5 times the log base 2 of 2. There's a lot of discussion in period 5 about where that times happens, and I want you to see this as a single log expression. You won't always write those parentheses down, but they are there. I'm going to erase this on the right here now. What is happening, if you are a little bit more movement-oriented, and I am, is this 5 is sort of interchangeable about whether it's a coefficient of the log expression or whether it's an exponent. And this is where it gets weird. Because the log law is that the log base b of x to the a is the same as a times the log base b of x. And the way that I kind of say this is that when you raise a power to another power, you multiply the powers. Here I'm raising an argument to a power. The raising becomes multiplication. That's the weird part here. And multiplication can become raising. It's interchangeable. We're going to work with this one for a little bit here. Let's do some little minor examples of how this works. The log base 10 of root x. This is one of the neat things about this. We get this expression a lot in calculus. And if I leave it like this, it's complicated. But if I pull out a constant, it becomes a lot easier. This is the same as the log base 10 of x raised to the 1/2, which is the log base 10, which is 1/2 log base 10 of x. And now that 1/2 could be something. Let's do the log base 10, 73, I'm just picking a number, of the 4th root of 125. And let's try to bring that down to a simpler argument. 5 to the 3/4, good. This is log base 73 of 5 to the 3/4, which means that this is 3/4 log base 73 of 5. You may ask why that is simpler, and I'll kind of explain this. I consider that to be simpler because if you had a table of values that express the log base 73 of 5, you could figure out what this is just by multiplying that by 3/4, which is a lot easier to do by hand. You divide by 4 and multiply by 3. That's not terrible to do to a decimal. But this is terrible. I want to kind of preview this a little bit because this process of going from here to here, it means this. Let's say I wanted to figure out what the 4th root of 125 is. Well, I could make it the log of the 4th root of 125, then find 3/4 of the log of 5, have a decimal for that, and then convert it back without the log. Just do 10 raised to that power. And that may seem more complicated unless you, again, devices and instruments and measuring things that let you figure that out pretty quickly. This is the basis behind basically all of 1960s and earlier math. This is how these techniques are how we built objects that put humans on the moon in 1960s. So the precision can be extreme. And this is all from non-computer-based reasons. So some of this is a little history of the math. Some of this is techniques that you're going to be using much, much, much later in classes that require them, because you'll need to be able to break things up into smaller pieces. Yes, Eli?
What happened after 1960? That changed out your calculator? Or?
Yes. Calculators, miniaturization was the thing. So pausing here for just a second. Okay, back to this. Your next set of directions are to express as the log base 2 of m and the log base 2 of n. So I like to think of this as a bad relationship tactic. We are breaking things up. Log base 2 of m to the 5th, n to the 7th. And I want to break this into simpler logs. The reason this might happen is because if I'm going to put things into a mode that is very calculator ready and very efficient at being done by hands, I actually want to break them up into smaller log expressions. So what I'm going to do here is I'm first going to see that there's a time sign in between the m to the 5th and the n to the 7th, which means that this is the log base 2 of m to the 5th plus the log base 2 of n to the 7th. Little misconception alert on the right side here. Hang on just a second, and I'll get right back. There is no such thing as a distributive property of logs. So the log of x plus y is not the log of x plus the log of y. This is another killing puppies mistake, like squaring across addition subtraction, radicaling across addition subtraction. There's only one operation you can do across addition subtraction, and that is
Addition.
no, addition you don't add across. If I take x plus y plus 2, I don't add it to both of them. What's the operation that distributes across addition subtraction? Multiplication. Multiplication division, but really they're the same thing. So this is not a thing. But back to this. This is almost simplified, but what can I do further?
Oh, you can make the m on the side. I mean, 5.
Yeah. We can bring that down. This is 5 log base 2 of m plus 7 log base 2 of n. While this is the answer for the question that was being asked, you very easily could be asked the reverse, which we'll do here in a minute, to go back to a single log expression, to basically squish everything down so that it is one log. Let's do some more breakups, though. Log base 7 of m root m, n squared, cubed root of n. And we'll just do a times 49 in there for kicks. My favorite expression. So breaking this up means you have two options here. If any of you are looking at this and saying, well, that's just m to the 3 halves, good. You're going a little shorter than you have to. You're taking some shortcuts, and that's fine. Just like this right here would be n to the 2 plus a third. But you don't have to 7/3. I can break this up right now and just make it log base 7 of m plus log base 7 of root m plus log base 7 of n squared plus log base 7 of the cubed root of n plus log base 7 of 49. Everywhere there was a multiplication, and there were 5 of them, we just broke up. Every one of these has an exponent that can come out to the front. The log base 7 of m has an exponent of 1. I can write that as 1 times, which just means I'm not writing anything. What's the exponent on this next one? 1/2. Log base 7 of m plus 2 log base 7 of n plus, what's the exponent here? Plus, can we simplify this? 2. Just 2. And hey, if you really want to, write that as log base 7 of 7 squared. Bring the 2 out in front. You have 2 log base 7 of 7, and we'll make that 1 in the next step just for fun. Can we combine like terms here? 1 plus 1/2? Combine those, 2 plus 1/3. 7/3. Log base 7 of n plus 2. So that is splitting this up as much as possible while still keeping like terms added together. Let's do more. Log base 2 of 1 over m squared n. Okay, on this one, you can do a few things. I'm going to show you one method, which is just to break it up as it is. Log base 2 of 1, which was the numerator, minus log base 2 of m squared. What's the very next symbol we're going to put in? Is it plus or is it minus? It is minus. Why? We're dividing by an n. That n's in the denominator. I'm minusing by the n. And here's why. A couple of ways I can show that. Let's say that I happen to write this as the log base 2 of 1 divided by m squared divided by n. You see how the divisions are now being converted into subtractions. What is log base 2 of 1, by the way? 0. Minus 2 log base 2 of m minus log base 2 of n. And we can erase that 0. Did anyone think to make this expression become the log base 2 of m squared n to the negative 1? And bring the negative 1 out as a negative? And that's where your two negatives here can also come from? Okay. Next set of directions. You're going to see the directions that say to write as a single logarithmic expression. I'm just going to use the words combine. Combine, squish, make it 1. Okay. Log base 3 of x minus 1/2 log base 3 of y plus 3. Let's leave it as plus 3. So bring it together as a single logarithmic expression, which means you're going the reverse of everything we just did. First thing, take your coefficients. Take these things and move them as exponents. So this is the log base 3 of y to the 1/2 plus, ooh, that 3 is just so awkward. If only it was a log base 3 of something. Log base 3 of 3 to the 3rd. I like that. And actually, if you really want to do a step before that, you could put it as 3 times log base 3 of 3, because what I'm going to write here is in a log base 3 world, 1 is equal to log base 3 of 3. So this means that there's an invisible 1 right here that we're going to make become this log base 3 of 3. And the next step, we can move that up, if you want, as an exponent. But let's try to squish this all now in one step. Log base 3 of, look at what I'm adding. Those all go in the numerator. We have an x. And what would this exponent really make this? 3 to the 3rd? 27. No, remember, Hannah, this is becoming the log base 3 of 3 cubed, which is going to give you a 27. So this is giving me a 27 in the numerator. And we have this x divided by what? Root y. Don't rationalize, please don't. That's yucky. Okay. Next one. I'm going to want you to do this and a lot of these now in one step. No intermediates. So let's kind of make one log expression. When I don't write a base, I assume a base. So can we write the log of a single thing? What's being multiplied, what's being subtracted, or added and what's being subtracted? What's my numerator going to be? A and C squared. Over B and B cubed. Okay, next, I want you to simplify this down to a single number. 2 log base 4 of 32 minus log base 4 of 8. So what we're going to do here, let's see if we can bring this 2 up. Log base 4 of 32 to the second. I'm not going to multiply that out, and don't. We always want to bring things down to simple bases because we're going to do that divided by what? 8. This means it's the log base 4 of 32 is 2 to the 5th squared over 2 to the 3rd. Which means the whole thing is 2 to the 5 times 2 minus 3, 7. So now I'm just going to ask you the question, 4 raised to what power is 2 to the 7th? 4 raised to what power is 2 to the 7th? Or 2 to the 2x equals 2 to the 7th? And my number, my single number, remember I stuck that x in artificially. I was just bringing everything down to one number. That one number would be 7/2. Okay, one more problem I didn't have time to get to in the other period, but we're going to do it on you guys, is a solve. Log base b. Oh, let's have some fun. Let's do the natural log of x equals 2 times the natural log of 4 minus 3 times the natural log of 3. It is. It is. ln is a log of a different base. You treat it, guys, treat it exactly the same as if you were to write log. I just want you to get used to seeing it. Exactly the same. Okay. So left side, we have the natural log of x. I'll write the parentheses because that may help your mental separation. What happens here? 4 squared minus natural log of 3 cubed, which means the natural log of x is equal to the natural log of 16. What do I write? 27th. So what's x? That's all there is to it. Okay, done for now.
Bye, Ben. See you soon.
Bye, Ben.